Okay, this is question number 1. 2 moles of a gas undergoes expansion from 5 liter to 10 liter against a pressure of 2 atmosphere at 25 degrees Celsius. The work done in this process is. Okay, so here while reading the question you should be little careful. It is given that 2 moles of a gas undergo expansion from 5 liters to 10 liters. So initial volume V1 is 5 liter, final volume is 10 liter, and it is given that against a pressure of 2 atmosphere. If it is given like this, against a pressure of 2 atmosphere, that means pressure remains constant. So here external pressure, against means external, okay. The gas is expanding against some pressure, there is nothing but external pressure. So external pressure is 2 atmosphere and it is a constant. See, it is expanding against a pressure of 2 atmosphere. That means the pressure, external pressure remains constant here. Okay, and you know very well, whenever the external pressure remains constant, that process should be an irreversible process. So it is an irreversible process. Okay, so it's an irreversible process. For irreversible process, you know very well, the general work done formula is integral V1 to V2, pressure volume work done, minus external pressure into change in volume. This is general formula. Now, in the case of irreversible process, pressure remains constant. Since external pressure is constant, you can take it out. So minus external pressure integral V1 to V2 into dV. Integral dV is V, upper limit is V2, lower limit is V1. Therefore, we can write external pressure into final volume V2 minus initial volume V1. This is the work done formula for irreversible process. Okay, whenever the process is irreversible, then this is the work done formula. Here V2 is final volume, V1 is initial volume. So now W is equal to minus external pressure is given, which is 2 atmospheres, into final volume is 10 liter, initial volume 5 liter. So 10 minus 5 is 5, 5 into 2 10. So you will get minus 10. This volume unit is liter, pressure unit is atmosphere. So we will get the answer as minus 10 liter atmosphere. Okay, you have to convert this 10 liter atmosphere into joules. See, in options, liter atmosphere unit, one option is with liter atmosphere unit, but here it is given 20 liter atmosphere, but the answer we got is minus 10. So option B cannot be the answer. The remaining answers, see, all the 3 remaining answers, options have joules. So we should convert liter atmosphere into joule. Remember, 1 liter, let me write here, 1 liter atmosphere equal to 101.3 joules. This is a standard value, try to remember this. 1 liter atmosphere equal to 101.3 joules, 101.3. Okay, so if I multiply this by 101.3, I will get the answer in joules. So minus 10 into 101.3, if I multiply, I will get minus 1013 joules. This is the work done in this process. So the correct option for this question is option C. Okay, yeah. Now let me move on to the next question. Question number 2. Just go through the question. For a van der Waals gas, dou U by dou V at constant temperature is equal to change in internal energy with respect to volume at constant temperature is equal to. Okay, right. For van der Waals gas, okay, before going to see van der Waals gas, let me give you the general formula for dou U by dou V at constant temperature. Okay, you know very well, according to standard thermodynamic equations, dou U by dou V at constant temperature equal to, this is actually a standard equation, try to remember this, T into dou P by dou T at constant volume minus P. Okay. With respect to internal energy, we have one standard equation. With respect to enthalpy, we have another standard equation. So this is one of the standard equation. So if you want to calculate this, you just calculate this and this, multiply these two, then subtract the pressure. Okay. Now, for van der Waals gas, okay, for van der Waals gas, what is the equation of state? Equation of state is P plus A n square by V square into V minus NB equal to nRT. Okay, so first we need to find out this quantity. For this you require pressure. So from this we need to find out an expression for pressure. Okay, how to do that? First bring this V minus NB to the right hand side. So P plus A n square by V square equal to nRT by V minus NB. Now bring this plus A n square by V square to the right hand side. So P is equal to nRT by V minus NB minus A n square by V square. This is the expression for pressure. Now what to do? Differentiate pressure with respect to temperature, keeping volume constant. So dou P by dou T at constant volume equal to, so number of mole is constant during any here the change in internal energy is given. They did not mention anything about the number of moles, so you should keep number of mole constant. Okay, number of mole constant, R constant, then volume also constant, B is van der Waals constant, right? So except T, all other things are constant here. So keep them as such, nR by V minus NB. Now if I differentiate temperature, I'll get 1. Here all the terms are constant, so it becomes 0. Therefore what we get is nR by V minus NB. This is the value of this differential quantity. Now therefore dou U by dou V at constant temperature equal to T into, in the place of dou P by dou T at constant value, I'll place this value nR by V minus NB minus pressure is there. This is the expression for pressure for van der Waals gas. So let me substitute that here, nRT by V minus NB minus A n square by V square. See here, see, we have nRT by V minus NB. If I multiply this by minus, I'll get minus nRT by V minus NB. So these two cancel. Then minus of minus become plus. So you'll get the answer as plus A n square by V square. So remember, dou U by dou V at constant temperature for a van der Waals gas is equal to A n square by V square. So for this question, the correct option is D. Okay. Whereas this is an additional information, keep this in mind. In the case of ideal gas, you know very well, internal energy depends only on temperature, If temperature constant, there is no change in internal energy for ideal gas. Therefore, for ideal gas, dou U by dou V at constant temperature equal to 0. Keep this in mind, very important. For van der Waals gas, this value is A n square by V square. For ideal gas, it is 0. Okay? Yeah. So, for this question, the correct option is D. Right? Now, let me move on to question number 3. Yes, go through the question. For a van der Waals gas, the change in internal energy during isothermal expansion from V1 to V2 is. Okay, listen, the general formula for change in internal energy, let me write the change in general formula. du is equal to, it's a very standard formula, n into CVM into dt plus dou U by dou V at constant temperature into dV. This is the general expression for internal energy. Okay, change in internal energy. This is applicable for any gas, real gas, ideal gas, solid, liquid, for any substance you can use. Now, it is given that change in internal energy, we need to find out change in internal energy during isothermal expansion. Isothermal means temperature constant. Okay, isothermal expansion is given, expansion. Isothermal means temperature remains constant. Temperature constant means d2 is 0. dt is equal to 0. Therefore, the first term which contains dt, that becomes 0. Therefore, change in internal energy du is equal to dou u by dou v at constant temperature into dv. This is the expression. And in the last question, we discussed that dou u by dou v at constant temperature for a van der Waals gas. Dou u by dou v at constant temperature for a van der Waals gas, it is equal to a n square by v square. So I'll put this value here. So a n square by v square into dv. This is for small change. This equation is for small change. For finite change, delta u is equal to, we need to integrate this, a n square by v square into dv. Here a is van der Waals constant, n is number of moles, that is also constant. Okay, so you keep a n square out, and integral, since it is expansion, for expansion and compression, the limit is supposed to be v1 to v2. In the case of expansion, v1 is small, v2 is large, into dv by v square. If we integrate this, what we get? 1 by v square on integration will give minus 1 by v. Upper limit is v2, lower limit is v1. So a n square to, okay, I'll take the minus out, minus. So we have 1 by v here, 1 by v2 minus 1 by v1. If we bring minus inside, I can write this as a n square equal to, if we bring this minus sign inside, this become minus and that become plus. So we get 1 by v1 minus 1 by v2. This gives you the change in internal energy for a van der Waals gas under isothermal expansion. Okay, note down, very important. Under isothermal expansion, the change in internal energy for a van der Waals gas, okay, you can calculate using this formula. So the correct option for this question is option D. Okay, take note. Now let me move on to the next question. Question number 4. Yeah, it's a very simple question actually, very basic question. A system absorbs 20 joule of heat. Absorb means Q should be positive, so plus 20 joule, and delivers a work of 30 joule. Delivers means work is done by the system, that means W should be negative. If work is done by the system, system delivers work means it is work done by the system, so you should put minus. We need to find out change in internal energy. So according to first law of thermodynamics, we know very well, change in internal energy delta U is equal to Q plus W. Okay, so Q is plus 20 joule plus work done is minus 30, so you will get the answer as minus 10 joule. Okay, so change in internal energy is minus 10 joule. That means internal energy of the system decreases, minus indicate decreases by 10 joule. Okay, so the correct option for this question is option C. Right, just use first law of thermodynamics and calculate. And you know very well, when a system absorbs, plus, when a system release heat, minus, when work done by the system, minus, if work is done on the system, plus. So sign convention and all you know. So this is how you should do this problem. Okay, right, let me move on to the next question. Question number 8. 8 moles of an ideal gas. Okay, it is given ideal gas. Number of moles is 8 moles. Consists of linear triatomic molecules. Okay, so let me write that molecule as A, B, C. It is linear triatomic molecule. We need to find out heat capacity at constant volume. This is what we need to find out. Okay, number of moles is given 8 moles. And one more information is given, vibrational modes are also active, so you should consider vibration also. Okay, we know very well translational kinetic energy. translational kinetic energy according to equipartition theorem. For any molecule, there are 3 modes of translation. So 3 into of nRT. This is the energy per mode, per mole. Energy per mode per mole. Since there are 3 translation modes, 3 into this. So you will get the answer as 3 by 2. Number of moles is given 8 moles. Okay, in the problem, number of moles is given as 8 into R into T. So we will get the answer as 12 RT. 2 to right, 4 to 8, 4 into 3, 12, 12 RT. So this is the total translational kinetic energy. Now, what is the rotational kinetic energy? Rotational kinetic energy. And here the molecule is linear. For linear molecule, there are 3 rotational modes. Keep this in mind. For any linear molecule, number of rotational mode is 2. For non-linear molecule, it is 3. Okay, so number of rotational mode is 2 into, for each rotational mode, the energy is of nRT. So we get answer as nRT. N value is 8, so 8 into RT. This is the rotational kinetic energy for the molecule or for the gas. Remember, I am using equipartition theorem here. Why I am using equipartition theorem? Because the given gas is ideal gas. Equipartition theorem is applicable only for ideal gas. Keep this in mind. Then vibrational kinetic. Usually we won't consider vibrational kinetic energy, but in the question it is given clearly vibrational modes are active. So you must include that. Okay. Since the molecule is linear, number of vibrational modes, okay, we can find using the formula 3n minus 5. There are 3 atoms. So n value is 3. N is number of atom in one molecule. N value is 3 now. 3 into 3 is 9. 9 minus 5 is 4. So there are 4 vibrational modes. And for vibration, each mode energy is, for each mode, energy per mole is nRT. It is not half nRT, it is nRT for vibrational modes. Therefore, you will get the answer as 4 into number of moles is 8 into RT. 8 4s are 32. So 32 RT. Now, what is the total internal energy? Total internal energy equal to sum of all the 3. So 32 plus 8 40. 40 plus 12 52. So 52 RT is the internal energy. But they are asking heat capacity in this question. So heat capacity at constant volume is equal to change in internal energy with respect to temperature at constant volume. We have to differentiate this with respect to temperature. So if I differentiate, I will get 52R is constant, keep it as such. If I differentiate temperature, I will get 1. So the answer is 52R. Okay. So for this question, the correct option is option A. In option A, 52R is given. Okay, take down. Now let me move on to the next question. Question number 6. Just go through the question. For a closed system containing a pure gas, dou H by dou P at constant entropy equal to. Okay, so system is a closed system and there is a pure gas, and you know very well, in the case of closed system, change in enthalpy, you can write change in enthalpy directly using standard equation, right? So according to standard thermodynamic equation, dH is equal to TdS plus VdP. It's a well-known formula. This formula is applicable for closed system containing pure gas. Okay. Now we should keep entropy constant as, okay, so they are asking dou H by dou P, how enthalpy change with respect to pressure, keeping entropy constant. Okay, if we keep entropy constant, see, if S is constant, that means change in entropy equal to 0. So this becomes 0. Therefore, dH becomes equal to V into dP. Okay, bring this dP to the left hand side. So I can write dou H by dou P. We kept entropy constant is equal to V, right? So they are asking dou H by dou P at constant entropy. So dou H by dou P at constant entropy is equal to volume of the gas. So the correct option for this question is option B. Very simple question, but you should remember the standard thermodynamic equation. Okay, there are four standard thermodynamic equations, right, are available. Let me write here. Change in internal energy equal to TdS minus PdV. Change in enthalpy equal to TdS plus VdP. Change in Gibbs free energy equal to VdP minus SdT. Change in Helmholtz free energy equal to minus SdT minus PdV. Remember all the four expressions, which are all very, very important. Okay, based on this, they may ask any questions like this. Okay, it's very simple to answer, right? Okay, now let me move on to the next question. Question number 7. For a closed system containing a pure gas, Cp equal to, they are asking heat capacity at constant pressure for a gas. We know very well Cp is nothing but dou H by dou T at constant pressure. Okay, just check the options. In option A, I don't have dou H, but in option B, I have dou H, but dou H by dou T should be there, but dou H by dou V is there. So option B is wrong. Cp, actually Cp equal to N into Cpm. Okay, this is heat capacity for 1 mole. If you multiply this by number of moles, you will get heat capacity for N mole. Okay, Cpm by N is not equal to Cp, that is wrong. And remember, heat capacity values are always positive, cannot be negative. So here we are using absolute temperature. Absolute temperature value cannot be negative. Therefore, T in minus T is always negative value. Cp cannot be negative. Okay, therefore this is also wrong. So the only possibility is option A. But how to get that? Remember, as per standard equation, right, just now we discussed, as per standard equation, dH is equal to TdS plus VdP. Now see here, we should keep pressure constant. If we keep pressure constant, this becomes 0. So dH is equal to TdS. dH equal to TdS. In the place of dou H, I'll put this TdS. So what we get is Cp equal to, I'll keep temperature out, ds by dou S by dou T at constant pressure. Cp is equal to T into dou S by dou T at constant pressure. This is another way of getting Cp. Okay, but this equation is valid, is very applicable in this case. See, bring this T this side, Cp by T, and bring the dt this side, Cp by T into dt, which is equal to ds, or delta S is equal to integral Cp by T into dt, okay, from T1 to T2. Listen, this is applicable, right, to find change in entropy when we carried out isobaric heating or isobaric cooling. Isobaric heating or isobaric cooling. Okay, yeah, it's a very useful formula to find entropy change of the system. We get this formula from this particular expression. Okay, yeah, anyway, for this question, for the question asked here, for this question, the correct answer is option A. Okay, this is an additional information, keep this in mind. Now, let me move on to the next question. Question number 8. For a closed system containing an ideal gas, dG at constant temperatures. See, the standard equation dG equal to VdP minus SdT, and it is given that the gas is ideal gas and temperature is constant. Since temperature is constant, dt equal to 0. If dt is 0, then this term becomes 0. So I can write dG equal to VdP. Okay, and it is given ideal gas. For ideal gas, we know very well PV is equal to nRT, or V is equal to nRT by P. Substitute this V, nRT by P here. So what we get is dG equal to nRT by P into dP, or we can write this as dG equal to nRT dP by P. You can write it as d ln P. dP by P can be written as d ln P. Okay, this equation is applicable only for ideal gas. This is applicable only for ideal gas, right, at constant temperature. dG equal to nRT into d ln P, right? So the correct option for this question is option B. They are asking dG, so dG equal to nRT ln P, right? Now let me move on to the next question. Just go through the question. Cyclic integral of del Q reversible by T is, okay, del Q reversible means heat transferred in the reversible process. We know very well from second law, right, or from the Carnot cycle expression, right? Using the Carnot cycle, we get this expression that cyclic integral of del Q by T, del Q by temperature T is less than or equal to 0. In the case of reversible process, let me write here, in the case of reversible process, cyclic integral of del Q reversible by T, this is equal to 0. In the case of irreversible process, cyclic integral of del Q by T, for reversible process we write REV, reversible. For irreversible process we usually won't write, okay. If you write simply del Q, it means it is irreversible. For irreversible process, the cyclic integral value is less than 0. Okay, this is based on Clausius inequality. Okay, so cyclic integral of del Q reversible by T is equal to 0. Keep this in mind. And so the correct option for this is option A. Listen, one more information you know very well. I am going to write this del Q reversible by T as differential of some function, say entropy. I will replace this by ds equal to 0. Now cyclic integral of differential of any state function, you know very well. Cyclic integral of differential of any state function is 0. So entropy is a state function. Keep this in mind. Okay, and this is the expression for change in entropy, okay, for reversible process. Take note. Now let me move on to the next question, question number 10. If PV equal to constant, P into V equal to constant, then delta H of the process is equal to, for some process PV is constant, then delta H of the process is equal to, see, you know very well, H is equal to U plus PV and delta H is equal to delta U plus delta of PV. Change in PV, but now in the question it is given that PV is constant, P into V is constant. Since PV is constant, delta PV should be equal to 0 because P into V is constant, right? Therefore, you will get delta H is equal to delta U. Okay, so delta H of this process is equal to delta U, option D. Okay, take note. And here we did not mention that volume is constant or not. If volume is also constant, suppose here we mentioned P into V is constant, we didn't mention volume is constant. If volume is constant, then delta U is equal to NCVM dt. This is also correct. But in the question, volume is not constant, P into V is constant. So keep that in mind. Therefore, for this question, the correct option is D. Okay, take two. Yeah, I stop here. We'll meet with a few more questions in the next session. Thank you for watching.